My name is Vinitha Ranganeni, and today I'm going to be talking about effective footstep planning for humanoids using Homotopy-Class guidance. This is work I did at Carnegie Mellon University in collaboration with Dr. Oren Salzman and Maxim Likhachev. So humanoids have many applications, such as disaster relief, search and rescue, and home assistance. But these are very high-level tasks that we'd like our robots to accomplish. Before they can do this, they need to be able to effectively navigate through complex environments. So take this home environment, for example. We want the robot to navigate from its current position to this goal region denoted by the green cylinder. But this is a very difficult task due to the high dimensionality of the system, as humanoid robots typically have 30 or more degrees of freedom. A common approach to deal with this dimensionality is to first plan a path in a lower dimensional space induced by the robot's feet, as each foot only has 3 degrees of freedom, x, y, and theta. This task is referred to as footstep planning. This footstep planner can then be used to guide the full body planner. However, in this work, we just focus on footstep planning. So to be a little more specific about footstep planning, we start with the initial configuration of the 2 feet. And in every successor, when we're doing our search, we move each foot individually at a specific time. And then when we get a sequence of these footstep motions, we get a footstep plan. So there's been a lot of work related to footstep planning. And one of the first proposed approaches was to use A-star to plan around planar obstacles. However, the problem with this approach was that they use complex inadmissible heuristics, and these heuristics can guide the search into an area where they may get stuck at a local minimum. And manually crafting informative heuristic functions is very difficult. So an alternative approach to get informative heuristic functions but not having to manually design them, or to get a more efficient planner without having to go through the task of creating very informative heuristic functions, is to use anytime variants of A-star with simple to define heuristics. So these heuristics are often 2D heuristics, such as Euclidean distance or backwards 2D Dijkstra. And so backwards 2D Dijkstra heuristic is when you run Dijkstra search backward from the goal configuration until every node has been expanded. So then you get the cost to the goal. However, our planner runs in 6 dimensions, however our heuristic is in 2 dimensions. So what we want to do is define a mapping from X footstep, which is our 6 dimensions, and to our 2D workspace. And what we do is we average the X's and Y's of the centers of the footsteps, and this gives us a centroid in between the feet. And so this is the node configuration that we would query when getting our heuristic values. But the problem of using anytime variance is that it sacrifices optimality for speed, and it doesn't solve the problem of getting stuck in local minimum. So an alternative approach is to use learning methods to learn informative heuristics. But the problem with this approach is that it requires a very large training data set and a good feature set. So let's look at this example. Here we see in the blue and purple rectangles the expansions during the search, and it wants to take the shortest path to the goal, which is through this narrow region between the kitchen island and the chair. However, it's not feasible for the robot to fit through this region, and after expanding for a very long time, it eventually realizes that it has to go around the island to plan to the goal. However, this is very inefficient, and this is not what we want to happen. And instead, what we want is for it to immediately know that it should plan around the island to get to the goal. And this is what we do in our work. We create informative heuristic functions without manually crafting them. So we automatically generate them so that we can actually achieve this type of motion. Our key insight is that we can use desirable trajectories to guide the process of generating a footstep plan for a humanoid. So there's 3 major components to this process. First is collecting desirable trajectories, and we get these from a user. Once we get these trajectories, we have to represent them in a manner that we can actually create our heuristic functions from them. And the way we do this is extracting their homotopy classes, which I'll explain shortly. And finally, once we've gotten these homotopy classes, we use them to create our heuristic functions for our planner. So first, we'll start off with trajectory sketches. So let's take this 3D environment where, again, we have this humanoid robot and we want it to navigate to this goal region. What we do is we project this environment into a 2D workspace, and we give this projection to the user and ask them to draw us as many trajectories as they want, but trajectories that they think are desirable. Once we get these trajectory sketches, we need to extract their homotopy classes, and this is how we represent these sketches in a meaningful manner. So first, what is a homotopy class? Informally, 2 continuous functions are homotopic if they can be continuously deformed into each other. So here, curve gamma 1 and gamma 2 belong to the same homotopy class because they can be continuously deformed into each other. However, gamma 3 belongs to a different homotopy class because it will intersect with obstacle O2. So now we want to be able to uniquely define these homotopy classes. And the way we do this is, let's take this example where we have obstacles O1 through O5, a start configuration, goal configuration, and then a curve gamma. What we do is we select random points from these obstacles and we extend beams from them. These beams are non-intersecting and they have to be extended in the same direction. So we chose to extend them in the positive y. From here we need to represent the homotopy class, and we do this by defining a signature. And as you can see here, these beams have associated letters, T1 through T5, which are associated with the obstacles that they're being extended from. And a signature is just a sequence of these letters, and it tells us which obstacles it's passing over, in which order, and in which direction. So if we cross over a beam from left to right, we add the letter Ti to its signature, and if we cross from right to left, we add the inverse of that letter to our signature, or Ti bar. In this example, we pass over T2, T3, and T4 from left to right, and T4 and T5 from right to left. So then our signature becomes T2, T3, T4, T4 bar, and T5 bar. But if you notice, this is over here, we're around beam T4, we're passing over it and then back around. And this is as if we didn't pass over it at all. So we can actually reduce this signature. And the most reduced form of this signature we call our H signature. And in this case, it is just T2, T3, and T5 bar. And the way we do this is if we look at two adjacent beams, the beam and its inverse, we can remove them from the signature, giving us our most reduced form. And if two curves that have identical reduced signatures, if and only if, they are homotopic. So this is how we uniquely identify homotopy classes. So now we have our homotopy classes, and we need to create our heuristic functions. So the question is, how do we use this representation of homotopy classes to generate our heuristic function? And this is the contribution of our work, homotopy-based shortest path algorithm, or HBSP. What HBSP is a variant of Dijkstra's algorithm which gives us the shortest path within the specified homotopy classes. So HBSP constructs heuristic functions based off the homotopy classes of the sketches provided by the user. So if the user provides multiple sketches, each of those translates to its own homotopy class and its own heuristic function. And additionally, if a user provides trajectories or sketches that belong to the same homotopy class, HBSP only creates one heuristic function for that. So it doesn't allow repeats. And we run HBSP on a graph that we incrementally construct, and it's augmented by the homotopy classes. So this means that multiple nodes can have the same configuration but different signatures. So if we look at this example here, we have this node U with a configuration U and a signature U. If we wind around this obstacle, we have the same configuration for this node, QU, but we add T1 as we wind it around this obstacle to the signature. So this is an example where multiple nodes can have the same configuration but different signatures. And then finally, we run a single search backwards on the projected goal configuration, QG, and the empty set for our signature since we haven't started the search yet. And then we continue the search and we expand until every start configuration signature pair has been expanded. And so when I say start configuration signature pair, these signatures are defined by the homotopy classes that the user has provided. So if they provided 3 signatures, we'll have 3 nodes in our goal set that we need to expand. So let's see how HBSP works on a simple 2D example where we have obstacle O1 and O2 and our goal configuration is start configuration. And the user provides us this path. And this path says to strictly go beneath obstacle O1 and then over obstacle O2. So we begin our search over just like Dijkstra search. And here the colors represent the heuristic values. So green is the lowest heuristic value and then blue is slightly higher. So if we were to run regular Dijkstras, we would just continue expanding over this beam and we would eventually get to the start. However, because the homotopy class of this path provided by the user says to specifically go beneath obstacle O1, we cannot expand, HBSP does not allow expansions over this beam. Instead, in order to get to these nodes, you need to go underneath obstacle O1. So this is, at the end, when we run HBSP, is what our color map will look like, where green is the lowest heuristic value and red is the highest. And you can see that this color gradient follows the path that the user provided. However, we don't actually run HBSP to completion, and as I said earlier, we only run it until we've expanded every start configuration signature pair in our goal set. And so the reason why we do this is because since the graph that we're running this over is augmented by the Homotopy class, it's expensive to run it to completion. So we run it on demand. So when we run it the first time, it will look something like this, where we have these colored boxes, which are nodes that have been expanded, and the white cells are nodes that haven't been expanded. And so when we use this heuristic function in our planner and it queries a node that hasn't been expanded, we continue HBSP where we left off until that node has been expanded, and we return that cost as the heuristic value. And additionally, I'd like to point out that we don't actually care about the exact trajectory that the user has provided, because as you see here that this is a rather suboptimal path. What we really care about is the Homotopy class that trajectory is in. And we simply ask for the path sketch, as it's an easy way to provide Homotopy classes. And as mentioned earlier, HBSP only cares about the shortest path in that Homotopy class. So if we look at this black line here, this is the shortest path in the Homotopy class. So let's see how HBSP works together in an example with the humanoid. So this is the 3D environment we saw earlier, and then we're going to project it, and then we ask the user for trajectories. And so we have one that goes beneath the couches and one that goes between. And then from here, we create our heuristic functions. And again, here's a color map of the heuristic values, and notice that the gradient does follow the trajectories that the user has provided. So now we have multiple heuristic functions, and the question is, how do we use multiple heuristic functions? So we use an algorithm called multi-heuristic A*, and let's see how this works on a simple 2D environment. And let's say that these were the two trajectories. Sorry, yeah, these were the two trajectories that the user has provided. So what multi-heuristic A* does is it conducts multiple A*-like searches simultaneously, one with each heuristic function. So each trajectory that the user's provided corresponds to one heuristic function. So in this case, we run two searches simultaneously. And the colors are associated with the Homotopy class of the trajectories that the user has provided. So here we have one search, and here's another. So what happens in this scenario is that this search gets stuck because the robot cannot fit through this region. However, this search is able to reach the goal, and so this is the path that is returned by the planner. And additionally, I'd like to point out that the user cannot prevent a path from being found because multi-heuristic A* is complete. So if they were to only provide this heuristic function, even though that it guides the search through an infeasible region, multi-heuristic A* will eventually find a path to the goal. So now when we complete this and run multi-heuristic A*, we eventually get this path here because it's infeasible for the robot to pass through this very narrow region. So we ran a series of experiments in this house scenario. And so let's look at a zoomed in version to see exactly the queries that we ran. So we ran two sets of queries which just contain different start and goal configurations in the house environment. And we defined a complex query as one where between where the robot starts and the goal, there's at least one path obstruction. So in this case, the robot has to navigate between or around these obstacles. Whereas a simple query, there's no path obstruction between the start and the goal, and there's a relatively straight line path. And so we ran experiments on 20 complex queries and 20 simple queries. We additionally ran it on various sets of heuristics. So the first set is just the one 2D Dijkstra heuristic I explained earlier. Our set 2 is the Dijkstra heuristic and one homotopy-based heuristic, and our set 3 was the one Dijkstra heuristic and 3 homotopy-based heuristics. And as you see that each set we have an increasing number of heuristics, and we wanted to see that if we increase the number of heuristics, if this would affect our planning times. But first, let's look at the heuristic computation times. And so we compare them with the complex versus simple queries, and as we see that as we increase the number of heuristics, the time taken to compute our heuristic functions increases. However, this doesn't affect our overall planning times, and our overall planning times includes both the heuristic computation times and our planning time. So if we look here, on the y-axis we have S1, which is the one Dijkstra heuristic, and S2 we have on the x-axis, which is the Dijkstra heuristic and the homotopy-based heuristic, and we're comparing the overall planning times. And notice that the y-axis is logarithmic, and that these curves, underneath this curve here, we only have a 1 time speed up, and here we have between 1 to 16 times speed up, and so on and so forth. When we look at the simple queries, we don't see much of a speed up. In some cases, we don't see a speed up at all, and we takes longer, and this is because these homotopy-based heuristics are unnecessarily complex for these simple situations. However, when we look at the complex query, we see a significant speed up in planning times of several orders of magnitude. And so when we look at this same chart, but on the x-axis we look at S3, which has 4 heuristics, of which 3 are homotopy-based. Again, we see the same results for simple queries, but we see even improved results when we're looking at complex queries. So to summarize, we presented an approach for automatically generating heuristic functions given user-defined homotopy classes to effectively plan footstep motions for the humanoid robot. And we showed that informative heuristic functions does increase or speed up our planning time by several orders of magnitude in comparison to the baseline approach. So while this work is promising, we still have many future directions. First, we'd like to automatically generate homotopy classes, because in this work we focused on if we're given good homotopy classes, can we actually use them to improve the efficiency of our planner? So now that we were able to do that by constructing these heuristics, we want to be able to automatically generate these homotopy classes so we can take the user out of the loop. Secondly, we want to be able to provide homotopy-based guidance in 3D so we can be able to run this planner in more complex scenarios, such as with stairs and ladders. And if you notice in this work, we were really restricted to just flat terrain. And finally, we're currently extending this for planning for aerial vehicles. So here's a video of some preliminary work, and here we see our expansions for 2 heuristics. One gets stuck over here, but this one's able to get to the goal. And this is the cave environment that we're running this on. And then finally, we execute this plan and we see this UAV that follows the plan of the search that was able to reach the goal. And with that, I will conclude my talk and I will take any questions.
So thank you very much for interesting presentation. I'm interested, so this problem which you showed, calculation times, this is for footsteps planning, right?
This is for footstep planning, yes.
It's quite fast. I have additional questions. So if you have originally homotopy class, so can you use something like convex then?
What do you mean?
Like convex optimization?
I'm not sure. So when I guess you need a different representation of homotopy classes in that case, because here we're looking at beam graphs, and so the way we represent homotopy classes during our search is very different than if you were to do this for as an optimization problem. Okay. So if you had a different representation of homotopy classes, I think that would be possible.
And one more, how do you guide with, you said your algorithm is complete, so even if this is not possible solution through this homotopy class, it will find other solution.
Yeah,
so how do you guide like your search by this?
Sorry, what was the last
part?
part?
Do you guide your search by this homotopy class?
Right, so there's, here, let me. So here specifically, like let's say that we only provided this path, and this is the homotopy-based heuristic that we're providing. So there's more details about multi-heuristic A-star that I didn't go into, but multi-heuristic A-star takes in an anchor heuristic, and so this anchor heuristic is a consistent heuristic, in which case, if you notice, all the sets of heuristics we use had one Dijkstra heuristic, so that's the consistent heuristic we use. So if in this case, we only provided this homotopy-based heuristic, there would also be one more consistent heuristic, and so eventually, also because A-star is complete, it will be able to find a path to the goal. Does that make sense?
Yeah. Okay, thanks.
Mm-hmm.
So you said that this homotopy-class may not be applicable for trajectory optimization. Are you familiar with the work, I'm not with the name, the trajectory optimization by a guy in MIT, which actually exactly for humanoid robot, where he discretized the environment based on the convex obstacle-free discretization of the environment, and then it becomes a subclass of trajectory optimization. But I was thinking that exactly the Homotopy-Class would be the sequence of those, sub-problems, those discretization of the environment. That could be a direct application of this Homotopy-Class in in trajectory optimization. That was a comment, basically.
Okay. Yeah, I think it could be. I just think that the representation of the Homotopy classes may have to be different. So now we're doing a beam-based representation. So if you represent a Homotopy class as a path integrals, I think that might work better.
Thank you. Thanks the speaker.